Okay. So I want to start. Please, if you are not asking questions, please try to mute your mic. I can't so otherwise I'll just take you off. Okay. So maybe we can start. I think that's the number. Um, so yes, let me say this. Those that want to be using Android phone and those MacBook, the Microsoft team is for Microsoft. So it's either you use it can accept any email, but not operating systems which are Microsoft and Android. So you should communicate to your friends that that's the issue. I've not yet logged this and they can join. But then once you are using Mac or this iOS, it will you'll find unless you connect online. That is, you use the web, not the app. Okay. So or either you can also use the app and then also get that. A minute. Let me see if I can. But it looks like people are complaining of the link. Um, so I can only copy a link here. Let me see if I'm trying to share that. Not really. Hmm. Okay. So those that are complaining that they don't have or the link is not connecting, I'm sharing. If you have the app, you can also use the key code to open as well. So tell them if they want to use the key code, they can also use the key code instead of it. So I've shared that. Okay, now let's start. So I'll try to minimize that. Just close this one. Yes. So that is that we should just look at it. We are trying to name these inorganic compounds. And at least I remember trying to summarize that we said that every time there's a given compound, I hope you can hear me. You can hear me, just give me a thumbs up if you are hearing me. And okay, are you hearing me? Okay,
Yes,
okay, thank you very much. Yeah, so we said that if we have like an inorganic compound and you want to name that inorganic compound, there are some questions that we need to ask. So we ask if that compound contains metal. Well, if yes, that means that that compound, um, sorry, if yes, that means that that compound is an inorganic compound. If no, then it means that that compound is a molecular compound. Okay. Now we have to ask one step further question. Though some compound does not contain metal, for example, ammonium is not a metal, but then it is treated as an ionic compound. So if that compound contains ammonium, then we want to say that that is ionic compound. So if yes, that is ionic compound. But then if it is no, then we'll name that molecular compound. So just name that molecular compound. How do we give it a name? we want to count the number of electropositive elements, followed it by the number of electronegative elements. And of course, the electronegative, we are going to be negating that. So that's how we name that molecular compound. So for example, if I have, say, well, we can just create any kind of, compound. So say, for example, I have, say, S and then F, E6. Well, the electropositive is a sulfur, so this is sulfur. And then, well, we can choose to ignore the mono for the first electropositive, but then what follows is that we have the hexafluoride. So we have the hexafluoride. Okay, so we name that. Now, if it is ionic compound, you know, we ended up saying that it's ionic compound because it contains metal. So we need to ask one more question that, of course, does it contain, is that metal a transition metal? Is it a transition metal? And of course, if no, then just name it as ionic naming. And how do we name that? That is just name the cation, follow it by the anion, and that is all. So if it's not a transition metal, then just name it as a cation, follow it by the anion. But then if it contains a transition metal, then the next step is to be able to calculate. So we try to calculate the oxidation state. So calculate the oxidation state of that metal. Now when we finish, we then name that ionic compound by naming the cation, follow it with the oxidation state as a Roman numeral. Okay, so this is just the oxidation state which we calculated. But then we'll write it as a Roman numeral between the cation and then the anion. I'm sure you remember that's where we ended the last time. Okay, so that's how we want to name these compounds. Of course, the anion can be a binary anion or a polyatomic anion. And so we should be able to know what are these polyatomic anions. And I remember trying to, so for the binary, we are looking at those on the P block. Okay, the anions from the P block, if we have the periodic table, we are looking at the anions. So this is boron, then we have carbon, we have nitrogen, we have oxygen, we have the halogens, that is the fluorine, of course, the noble elements follow. So this is going to have a charge of -1, -2, -3, then the carbon is just going to be ±4. So we have these elements which are going to be the negative or the anions. So we can list them and try to see how they, so these just the element to form the binary anions. And so we know how to write the negative of these elements. So we end with the IDE for those binary anions. So if I want to list some of these anions, because I just saw that some of you are not quite familiar with these anions. So maybe if I start and then try to see if, so for example, if I have carbon and I want to make carbon a negative, then that becomes a carbide. Okay, that is we have in say C4 minus. It can sometimes also be C2 minus. If I have nitrogen and I want to make it negative, can somebody help me? If I want to make it negative, then this becomes the nitride. If I have, say, phosphorus, okay, if I have phosphorus, and then I want to make phosphorus the negative, that becomes phosphide. If I have sulfur, and then I want to make it negative, that becomes oxide. Are you following? If I have well, the halogens can be okay, fluorine, bromine, okay, bromine, and then iodide or iodine. Well, when you have the halogens and then you negate them, they become the halide. So you have, for example, the fluoride. Okay, we have the chloride. We have the bromide. Okay, we can have the iodide and those kind of stuff for the halogens. Well, if hydrogen becomes negative, so if hydrogen becomes negative, it is called a hydride. Well, these are the common anions that we have. That's the binary anions. Now, we can also look at the polyatomic, some examples of these polyatomic anions. So, for example, so if I'm putting the symbols there, nitride is N3 minus, phosphide is P3 minus, sulfide is 2, S2 minus, the halide becomes X minus, hydrogen becomes H minus. Okay, so note that. So that would be Cl minus, F minus, Br minus, I minus. That's the halide. Okay, so these are the binary anions. Now we can also look at the polyatomic anions, some examples of these polyatomic anions. I think you can give me some examples. So for example, NO2 minus, what is the name? That is the nitrite. When we have NO3 minus, that becomes the nitrate. I'm very sure you are taking notes of them. Of course, I can't list all of them, but just a few common ones. We can also consider that few common ones as well. We can look at, say, SO42 minus, that is sulfate. I listed some in the notes that I gave you, but then if it's good, we'll just go through some of them. So SO3, 2 minus will be the sulfide. Okay, will be the sulfide. Is somebody asking a question? Okay. Now we can have HSO4 minus. That anion is called the hydrogen sulfate. Hydrogen sulfate, or what you call the bisulfate. We can call it bisulfate. We are not far from the truth. We can have OH minus, which we call the hydroxide. Okay, hydroxide. We can have CN minus, which is called the cyanide. Okay, so cyanide. We can have P4 minus, that is the phosphate. Okay. When we add H to that, that becomes hydrogen phosphate. So hydrogen phosphate. And then when we add another two of that to that phosphate, this becomes the dihydrogen phosphate. Dihydrogen phosphate. Okay, we can list more. Well, I think CO3 2 minus, that is carbonate. And we add hydrogen to that, that becomes the bicarbonate. Okay, the bicarbonate or the hydrogen carbonate. What again? What an ion did I leave out? Okay, the chlorine, ClO3 minus, this is chlorine. When we reduce that to ClO2 minus, that becomes the chloride. I'm very sure you're paying attention. Okay. Now when we reduce it again to ClO minus, that becomes the hypochlorite. Because when we have more of that, so ClO4 minus, that becomes a perchloride. Perchlorate, rather. No, so perchlorate. Okay. We can list more. When we have, so say MnO4, that is what we call the permanganate. Permanganate. When we have, say, CrO4 with 2 minus, this is what we call the chlorate. Chromate. And then if we increase the chromium to 2, and then 7, 2 minus, this is the dichlorate. Okay. What again? Okay, CH3, COO minus, this is what we call the acetate. The acetate. Well, if it is organic, that becomes ethanoate. But then inorganic, we prefer calling it the acetate. Well, oxygen, when it reduces, the O minus can be the oxide, but then we can have the peroxide, that is minus, this is peroxide. Then we can have the superoxide, that is minus half, the superoxide. Well, what did have I left something out? Okay, another common one that, so if I have cyanide, I can have the thiocyanide. So CSCN minus, we call it the thiocyanide. So the thiocyanide is the SCN. We can also consider, so I think okay, let's go up. We can also consider the C2O4, 2 minus, which we call the oxalate. I think I'm almost through with the common one. Well, the last one, which I'll mention, is the thiosulfate. That is S2O3, 2 minus. That is thiosulfate. Okay, so at least I'm able to list the common polyatomic and then the binary atomic. So naming ionic compound, we name the cation, and of course the cation are just the metal names. Follow it with the anion. So the anion can be a polyatomic anion or a binary anion. So that's how we name the ionic and then the molecular compound. Now I want to move on and try to name acids and base. Now by definition, we have three, of course. One is not well considered. So we have acid and base, and by definition, we define these acids by 3 definitions. Number 1 is the Lewis definition. Number 2 is the Arrhenius definition. And then number 3 is the Bronsted-Lowry definition. So the BL definition. Well, Lewis, for example, Lewis acid says that these are compounds that have they accept electron pair. Okay, so electron pair acceptors are acids. Then electron pair donors will be bases. Now, Reynolds defined acid to be a substance that has hydrogen in that, and that hydrogen it can release. So hydrogen donors are going to be the acid, and then hydroxide donors, the compound that contain hydroxide in them are what he calls the base. But the Reynolds definition failed because it couldn't really account for, say, why ammonia is a base. Okay, so the Bronsted and Lowry definition then says that the acid is the proton donor and the base is the proton acceptor, so that it can capture the ammonia. So ammonia captures or it accepts proton and ammonium. So that it can just then address that. So we are looking at this, naming. For the Lewis naming, it basically follows the ionic naming of these compounds. So for example, iron oxide is just a base. So that's just that aluminum oxide, just like that. So we want to just concentrate on the Bronsted-Lowry acid, and then we'll also look at the base. So especially the Bronsted-Lowry, which it says that the Bronsted-Lowry acid is a proton donor. That means that the substance that has H plus to donate. So the proton donor. And then the base will basically be the proton acceptor. Okay, so these are the definitions which we want to look at. So basically what it means is that every acid should have hydrogen in that, according to Bronsted and Lowry. Now, how do we name these acids? Well, we can notice that the hydrogen can attach itself to just a single element that is a binary anion, and then we can also have the polyatomic anion. So we can have what we call the binary acid, okay, and then the polyatomic acid. And so let's start with the binary acids. How do we name binary acids? Say, for example, H and Cl. This is a binary acid. Well, IUPAC says that if you want to name them officially from the old, you see that old naming, you see these are molecular compounds, okay? And that this molecular compound, though it's covalent, behave like a dative. So it looks like this element want to pull and become negative, but that's not ionic. Now, if we are going to be naming it according to the molecular naming, we're going to say that this is hydrogen chloride. Was that correct? So that's, now if we want to name it according to acid, then for binary acids, you see they are going to be ending with IDE. And so what happens is that we'll change the IDE to IC and then add acid to that. Now, we also give a prefix by changing the hydrogen to just hydro. So instead of writing hydrogen, then we'll just write hydro for binary acids. Okay, so such a compound, we'll just say it is hydro, and then the chloride now is going to be changed to chloric, and then we add acid to that. Is that okay? Are you there? Okay. Now, for example, how do we name this compound HBr? Well, the hydrogen is there, so it becomes a hydro, and then the bromide now becomes bromic.
Hydrobromic.
And you add acid to that. So that's hydrobromic acid. Does it make sense?
Yes, please.
So say, for example, if I have another acid like, say, HF, what do you think will be that? That's just going to be hydrofluoric
Hydrofluoric acid.
Okay, so hydrofluoric acid. So that's the binary acid. Now, when we take the polyatomic acid, now the polyatomic acid, of course, contains hydrogen and then an anion, and that anion is a polyatomic anion. Now, how do we name them? Well, we'll notice that when I was listing the polyatomic anions, you could see that most of them are ending with ITE or ATE or ITE. That is the 8 and then the I. The binary ones end with the IDE. Okay, so when we want to name the polyatomic anions, those anions that ends with 8, what we do is that we replace the 8 with ICE and then add acid. Is that okay? Now those that ends with ITE, we'll replace the ITE with IOUS and then add the acid to that. That's the first step. And the second step, unlike the binary where we are bringing the hydro, for polyatomic acid, we choose to ignore the hydro and then we name the compound just by giving that or naming the polyatomic anion. So we ignore the hydro in there. For example, we have H2SO4. The polyatomic here is the sulfate. Okay, so what it means is that I'm going to replace this with the ICE and then I'll choose to ignore the hydro. So this becomes basically the sulfuric acid. Okay. If we have, for example, HNO3, what do you think would be the name?
That's nitrogen. So, hydro.
No, it's a polyatomic anion. The polyatomic anion is
Nitric
Nitric
acid.
Thank you very much. So when you want to name this becomes the nitric acid.
The nitric acid.
Nitric.
Okay. So for polyatomic acid, don't bring the hydro. But then when it ends with the 8, say for example, another example is H2NO2 or HNO2. The polyatomic anion is the nitrite. So this acid becomes the nitrous acid. Does it make sense? Perhaps it's outlining this. Help me name this. How do I name this acid?
Phosphoric acid.
Phosphoric. Okay, phosphoric acid. Why? The ion here is phosphate, and then that basically we just replace the H with the ink, and then we add acid to that. How about this acid? It's what?
Carbonic acid.
That is carbonic acid. So
Carbonic acid.
was the H, so that's the carbonate, and so we replace that with the carbonic acid. Is it making sense?
Yes.
Okay, how about this one? HClO2. What do you think will be the acid name?
Chloric.
It's what?
Chloric.
So come again.
Chloric acid.
Chloric acid.
This is the with the oil.
Chloride.
Let me
Yeah, chloric acid.
replace that with the ice, and so it becomes right a chlorous. How about this one? So
Wait, that's
HClO. What do you think?
Chloride.
Please check the ion very well. And the anion is
us.
hypochlorous acid.
Hypochlorous acid.
Hypochlor.
Chlorous acid. So if I want to summarize that, what I can say is this. So I just make a table quickly for that. And that once I want to name the acid, which is a polyatomic acid, then definitely, well, if it is binary, I just add hydro before changing that. So I make a table. I need to know the anion name when I'm naming the acid. Okay, so the name of the anion, so the name of the anion will give me the name of the acid. Okay, so for example, if the anion is something something, but then it ends with ATE, when I'm naming the acid, that becomes that something something, but then I'll end with IC, and then I add acid. When that anion is something something, but it ends IC, when I'm naming that, that becomes that something something, but then I'm going to be ending with the IOUS, then I add acid. That is the oil and then the ink. And so, for example, if I have the pair something something and then the H, it happens that it has the H, then of course it's pair that's something something, but then I'll end with the oic acid. If it is hypo
Sir,
and it ends with
sir,
ITE, I still have, let me land, I still have the hypo and then that becomes my oil acid. Yes.
sir, please. The name of the acid is not clear. We can't see.
Please, I can see. So please confirm for me. Those online. Yeah, I said I don't trust them. So I've also set my screen to monitor what is going on. So I've connected with. So please check yours. I can see people giving me thumbs up, meaning you have problem with your screen. Okay, and so that is just that I'm monitoring when there's any problem. I guess I can note. But so maybe you are using laptop or phone. Your phone, if it's not quite everything, will not give you clear, but laptop should give you quite an open business. Okay, so that's just that. Then, if it is a binary acid, you see, we'll be ending with the IDE. So how do we name that? That will bring the hydro, and then whatever anion is there, we'll just end the acid. So this is how we name acid. You have to know the anion name. Now the anion name will tell you whether it is ending with the ATE, ITE, or the IDE. When it is ATE, then we'll change the whole, remove the whole of the ATE, and then replace IC, and then you add acid. When it is ITE, you replace the ITE with the IOUS, then you add acid. So if the anion has the pair or the pairs, for example, perchlorate, if the anion is perchlorate, then the acid or the acid, so for example, if the anion is say perchlorate, hydrogen that's perchlorate, so then the acid becomes the chloric acid. So this becomes a perchloric acid. Now, if it is, say, the hypo, then say, for example, the hypochloric, So that's the hypochlorite. So the acid name becomes the hypochlorous acid. And of course, if it's binary, then we'll bring the hypochlorous in. Will we remember that? Will we remember?
Oh, what is that making noise?
Okay. So that's just that we can give names of these the acids.
Yes.
Okay. Yes, any questions? So that's how we name acids. For Bronsted Lorry bases, that is those species that can affect so those base species contains hydroxide or it does not contain hydroxide. So for naming of acids and base, I mean for bases, whether strong base or weak base, if it is a strong base,
Please, I have a question.
yes, go ahead.
My question is, when we were in SHS, we were taught that H2SO4 is called tetraoxosulfate 6 acid, and here we are saying that it is sulfuric acid. So I want to know the difference between them.
We are just going to be doing that very soon. So keep what you know.
Okay, sir.
That is when you don't know the anion name that is the sulfate. That's why you use the also name. We are yet to get to also name. So please put them one at a time. Yes, any other question?
Okay, sir.
Okay. So for bases, we can have the strong bases, which of course has the OH, and the weak bases are purely like molecular compounds. So naming of bases follows the ionic and then the molecular naming of compounds. For example, this is a base, and if you are naming this is ionic compound, so this becomes sodium hydroxide. So we name the strong base following the ionic name. So this is also a base, say for example, and that will become sodium carbonate. It's ionic. Now this is a base, a weak base, and the weak base follows the naming of the molecular naming, and so this becomes nitrogen trihydride. So it follows the molecular naming when it is a weak base, and then it follows the ionic naming when we are talking about strong bases. So that's how we name bases. So again, for bases, it just follows the ionic if it is a strong base, and then molecular if it is a weak base. Now the acid also follows such that if it is a binary acid, we bring a prefix of hydro, and then we'll end with the ICE by replacing the IDE with the ICE. Now the polyatomic anions can be ending with the ATE or the ITE. When it ends with the ATE, we'll just replace with the ICE and then the acid. When it ends with the ITE, we replace with the IOUS, then we add acid. So that's how we replace or we just form or we just name the acid and then the bases. Another common inorganic compound is hydrates, compounds that contain water in them. So if you have heard hydros or anhydrous, that is against water, and then the hydrates. So compound that contains water, we call that the hydrates. Now, how do we name hydrates? Well, naming of hydrates follows the ionic naming. But then when we are finishing, we need to indicate the number of water molecules that are present, again using the mono, di, tri, and those curves. But then we end it with the hydrate. So for example, if I'm having any inorganic and that is an ionic compound, I name that ionic compound now, follow it by the number of the water molecule. So this ionic compound, follow it with the number of ionic. So that's the number of water, which is like when it is one mono, di, tri, and those stuff. So for example, if I have this SO4 and the water molecule here is 5 of that, well, we say that we follow the ionic naming for the salt, but then we add the number of water molecules as the hydrate. So how do we name this ionic compound? Well, copper is a metal. Of course, it's a transition metal. If the sulfate is 2, then this becomes copper, so the oxidation will be 2, and then the sulfate. So well, that's the ionic part. Then once you are not cautious in muting yourself, I think I'll mute it, but then the next time I see that Muhammad Zina, I'll just remove you from the group. Okay. And that is 5 is penta, and so this becomes pentahydrate. So we name the ionic part, and we follow it with the number of water molecules as a hydrate that is there. Sorry, so don't think you want to change the name. Some people are outside this organization and are having access to that. Okay, I guess maybe we'll share the link. Okay, let's move on. Okay, so then how do you think we should name this hydrate compound? KBr7H2O. How would you name that? Can you hear me?
Potassium bromate. Heptide.
So that is
potassium bromide, potassium bromide, heptahydrate.
Okay. So you don't tell me, but then name the.
I agree.
TrCO4. H04. We have FeClO2, and we have 4 water molecules. Well, I can write the name so that you write the formula. So, for example, barium iodide dihydrate. Can you write the formula for me? So barium iodide, what will be the formula? Well, barium is Ba. Okay, iodide is just 1, so group 2. That's why we didn't calculate the oxidation state. So this is barium iodide, and then 2 hydrates.
H2.
Okay. Now, how about this one? What's the anion here? Anion.
Chloride.
Hypochlorite.
Hypochlorite.
How do we name that? What name do we use?
Hypochlorous. Ion. Hypochlorous.
chloride,
Hypochlorous.
and then the water molecule, so that becomes the tetrahydrate. So ion hydride. How about biology? Phosphate. Phosphate has an oxidation state of NH3, so therefore the chromium becomes chromium 3, and then chromium 3 phosphate, and then the water dye. I will, is that, please confirm. So that's how we name the hydrate. So we name it following the ionic naming, where we name the ionic compound, then we follow it with the hydrate. But this time in the hydrate, you count the number of the number of water molecules that are there, and indicate whether it's mono, di, or tri, tetra, whatever, to the infinity. Is it making sense?
Yes, sir.
Okay. So let's see the last one if it makes sense for you. So this is NMNO4. Then we have this water molecule there. What does that mean?
Sodium permanganate.
We want to name this sodium what?
Half minute. Pero.
Sodium manganate.
Manganese. And then that half is hemihydrate.
Hemihydrate. Wow.
Manganese.
Sodium permanganate. Wow.
And then water molecule here is hemi and then hydrate. Is that okay?
Yes, sir.
We make another step. Okay, so moving forward, there were some these polyatomic anions that have oxygen in them. And so we want to see how we name these so-called oxo compounds. So oxo compounds. And of course, oxo compounds are these compounds that contain or that has a component of oxygen in that compound. And so the oxygen we shorten to be the oxo. The oxygen part is what we are calling the oxo part. So normally it has kind of an element that is attached to that oxygen. So let's look at naming of these oxo anions before we come to the naming of the compound itself. So how do we name oxo anions? So for example, we have say PH3 minus. This is an anion. Well, the common name for this anion is phosphate.
Phosphate.
Now, if we want to name phosphate as an oxo, then I say that we need to keep the number. Then we follow that with the element that is attached to the oxygen. So name block so that the element that's attached to the oxygen. The next step is to calculate your. When I'm using your new system, well, I only have that patient to be delete from the platform. So please, Mike, if you are not asking, to ask a question you answer, you can just unmute answer and then mute it back. Paying attention to that will help you. Okay, I'm not sending the warning again. The next time you just drop and I'll log the class. Okay, so while we try to name the oxygen first and follow it with the element that is attached. By this time, we need to calculate the oxidation state of the element that is attached and put it as a Roman numeral at the end of that element. So in this first step will mean that we are going to be naming the oxygen and then follow it with the phosphorus. Now the phosphorus becomes phosphate. Now we need to count the number of oxygen, and the number of oxygen here is 4. So this becomes the tetra, and now we shorten the oxygen to call it the oxo. Then the phosphorus we make it negative to become the phosphate. So for oxo compounds or oxo anions, all of them are going to be the 8. So we make it that 8. Then we'll calculate the oxidation state for the phosphorus in this case. To look at it, this is -2 times 4 -8. It crosses here. What will be the oxidation state of the phosphorus? -1. Come again.
5.
Who said 1? So that is +5. So this becomes 5, and then of course we add ion. If you don't add the ion, then it's taken as a compound. So if you don't add the ion whilst it is an ion, that is wrong, because it is then going to be treated as a compound. So then the name for this anion will be the tetraoxo-phosphate ion. Another example, if I have, say for example, SO4 2-, and somebody guess how the name is going to be like?
Tetra sulfate 6 iron.
This is going to be also
Iron.
4, and what the oxidation is
Six iron.
-8. That's going to
6 iron.
be 6. So this one becomes iron. So tetraoxosulfate 6 iron. But I give a lot on this, you are following that. So say NnO4-. Well, how do we name
Tetraoxomanganate 7 iron.
so the oxidation state here is +7. This one becomes a tetraoxo
Also, manganese 7 iron.
manganate
Iron.
7.
7 iron.
Is that correct? Okay. Now, so how about this one? If I write CO3 how do I name that?
Triosocarbonate 4 iron.
Iron.
Carbon here
Diazocarbonate 4 iron.
+4. So that would be carbonate 4. So carbonate 4 ion. I hope that is okay.
Yes, sir.
Okay. Now let's look at naming compound. Of course, if you don't bring the the ion there, we treat it as a compound. Now naming a compound, say for example, KMNO4. Well, the IUPAC naming will be different because, of course, here it's an ionic compound. So basically, I'll just say this is potassium permanganate. But then I can also use the also compound, also name it to name this compound. And that I name the cation first, which is the potassium, and then the anion will follow. But then the anion follows such that I name it as oxo, naming as the oxo anion naming that I name. So like this. So then the tetra oxo oxygen and manganate. So manganate. And then if you look at the manganate here, this becomes a manganate. And of course, that is the compound. So I just leave it like that, or I can write compound at the end. So this is potassium tetraoxomanganate 6. Is it 6 or 7? Manganate 7. Then I add 7. Does it make sense?
Yes, sir.
Yes, sir.
Say, for example,
Yes, sir.
CO3. Well, ionic naming is just calcium carbonate, simple. But then if I want to use the other naming, how do you think I should name this? This becomes a cation, which is the calcium, follow it by the anion. Now the anion now becomes a trioxo, and then the carbonate. Now I calculate the oxidation state for that, and that is carbonate 4. So the calcium trioxo carbonate 4 compound. Does it make sense?
Yes, sir.
We can equally
Yes, sir.
name the acid and the base as the same. So for example, this was just the nitric acid, just like that, nitric acid. Now, if I don't know the anion name, I can use the also naming to also name this compound. Okay, so this then, of course, in polyacid acid, we don't consider the hydrogen. So definitely what I'm just going to do here is just going to be the trioxo, and then the nitrogen attached to that becomes the nitrate. And then what's the oxidation state for that? That's minus that plus
5.
equal to so that's 5 crosses to there becomes plus 5. So this becomes trioxo nitrate 5, but then we acid to 8 to indicate the hydrogen. If I don't add the acid, it becomes a compound. So
Question.
you help me name this acid. But that's sulfuric acid. But then if I want to use oxo naming, how do I name this? Yes, how do I name that?
The question.
Okay, I thought you answered that before you asked the question. Okay, ask your question.
Okay.
Ask your question before we answer that.
Okay. Okay. So please, the calcium triosocarbonate. You've written calcium triosocarbonate 6, but when you calculate for the oxidation state for carbon, you get 5. But you've written 6 as the oxidation state.
Which one are you talking about? IV is not 6, so VI is 6. IV is 4. So where are you seeing the 6? So IV
It's
is
5.
4.
You've written 4. It's 5.
Okay, so
No,
Say it's 5.
okay,
it's
so
4.
carbonate.
Calcium is 2.
Calcium is
Ah.
calcium
It's 2. It's plus 2.
and then we know that we have 3 of the oxygen. Everything should be equal to 0. So it's 4. Where is the 5? So 2.
I thought the calcium was 1 rather.
No.
Calcium, so that is 2. Sodium is 1. Potassium is 1. Calcium is plus 2.
Okay, thank you, sir. Thank you.
So the madam that just asked the question, then can you help us answer this? H2SO4, how do we name using the also naming? So the common name or the IUPAC for naming acid will just be sulfuric acid. How about the oxo naming?
Can I answer that?
Can I?
Ask the question.
Okay.
Madam,
The answer is
answer it. Let's move fast.
tetraoxo.
Sulfate. 6 acid.
6 acid.
Six acid. So the sulfate here, hydrogen is 1 plus 1, that is 2. We don't know of sulfur, but then we know the oxygen is minus 2 and everything is 0. So this becomes 6. So sulfate 6, and then it is an acid. So if you don't add the ion, don't add the acid, then we treat it as a compound. So that's how we name, or the rules for naming these also compounds. Any confusion somewhere? So
Yes, sir.
the last one, let's try. So if the sulfite will change that to become the oil. So this becomes the sulfurous acid. But then if we are naming it as an oxo, then this becomes the trioxo sulfate. And what's the oxidation state for the sulfate here? What's the oxidation state? Sulfate
4 plus 4
acid. Okay, so
Yes, sir.
I plus 1 times 2, so minus 6, that's plus 4, it crosses to become 4. So I is 4. Is that okay?
Yes, sir.
Okay, so I guess from now, we should be able to approach or attempt any kind of compound that we come across. We should be able to name any compound that we come across. And of course, we can derive those compounds, the formulas that come together for those compounds to be formed, and then we can also name these compounds as well. So that's trying to study the matter. Now let's try to make one step progress, or if there's any question about naming, you let me know. Otherwise, find some examples and try to see if you can name those compounds. So when we say you should name whatever it is, you can come from the angle of just naming the article. If that compound contains the oxo, we can name that as the oxo compound and those kind of stuff. Now, what happens if the name contains more than 3 kind of elements? So, for example, before I move on, so for example, this is CHCl3. How do we name this compound? Well, clearly, this is not an inorganic. So we have 3 elements, and there's no way I've seen this as an ion. So this tells me this is an organic compound. There's no anion name like this. Well, I'll attempt naming it as just a molecular compound, but then it's going to be falling out of place for naming this as inorganic compound. So this is an organic compound. Then we have to use the organic naming to name this compound. Okay. Now again, when you are naming the oxo compound, we also compound when we have just one element attached to that oxygen. If it becomes 2, we can't name that compound as oxo compound. We have to name it as a molecular kind of naming. Are you following?
Yes, sir.
Yes, sir.
That is that. So basically, that is just that. Now, we now know the compounds and then their names that we give to this compound. Trying to study this matter, then definitely we should be able to, of course, it's to have mass or that. So now we can be able to quantify these compounds that we have. Okay, so we want to see how we quantify these compounds that we have. Well, we should know that compounds exist in phases. Right? So compounds exist in phases. We can have compounds in the liquid phase, and then in the gaseous phase. So the compound can be a gas, it can be a liquid, it can also be a solid. So we want to understand how we can quantify these compounds in their various phases. Now, the quantification of this compound is what we call moles. The fourth law, which I said we are now going to be expanding that. Now, moles is just trying to get the amount of the substance which is involved. Well, we just have a symbol we represent as mole. Now, by definition of mole, we are trying to compare the substance that we have. The amount of that substance is being compared to the amount of carbon-12. And the reason why we compare to carbon-12, of course, the mass of carbon-12. Number one, carbon-12 is mass stable element. It has an abundance of almost 98.9%. Number two, it's quite common, both in inorganic and then organic species. That is living and then non-living things. You can find carbon in non-living things, you can find it in living, whether organic and then inorganic. And it's quite common everywhere, easy to access. And so that's the element that we make reference to. And so a mole basically is just we're trying to know the amount of substance that contains the same number of entities. And these entities are, it can be molecules, it can be, say, sorry, I'll decrease this. Okay, so it can be ions, it can be atoms, it can be molecules. These are the entities. And that if you take any substance, then the number of entities are just these numbers. And we compare this, of course, can also be electrons, whatever. We are comparing these entities to carbon-12, and that we want the exact mass of carbon-12, and the mass of carbon-12 is 12 grams. So 12 grams of carbon-12 is what you are trying to measure as the amount of moles. Now, if I pick, say, 1 mole, it's equivalent to 6.02 times 10 to the power 23 entities in just that 1 mole. So the entities, and this is defined by Avogadro. So Avogadro gives us this condition that if I pick any amount, the number or the amount which is containing the number of entities which is equivalent to 12 grams of carbon-12 is 6.02 times 10 to the power 23 entities. Okay. Now the mass of that the mass of carbon is measured in the atomic mass unit. So all the elements will represent by the atomic mass unit. Now, if these elements come together to form these compounds, then we'll put their elementary or the atomic masses together to form what we call the formal mass. In other words, that is the molecule mass or what we call the molar mass. So if you put all the individual element masses together, it be formed or gives us the molar mass, which we express as gram in each molecule. So if I take 1 mole, it should contain this amount of that mass. And so we can just do some few kind of relation here. Now, if the compound is solid, it means that we can know the mass of that solid. We can weigh that mass, and so the amount of substance, which we call moles, we use the symbol N, is going to be the mass that we measured as compared to the former mass of that compound. So the mass over the molar mass is what we call moles. Does it make sense? So the mass, small m, we can measure. The big M is constant. Once I know the compound formula, I can know the molar mass, and so I can find the amount that is involved. I hope it makes sense. So with these 3 variables, we can just play with that. So for example, if I'm given a mass, so the mass of H2S, and what will be the name? What is the name of this compound?
Hydrogen sulfide.
Hydrogen sulfide. If you are using the molecular, that becomes dihydrogen monosulfide, and then the common name is hydrogen sulfide. So if I'm giving, say, 13 grams of this hydrogen sulfide, and then they ask us to calculate the moles of this hydrogen sulfide, how are we going to do that? Well, since I know that molecule and it is hydrogen and then sulfur, then the formal mass for this compound, or the molar mass for this compound, will be hydrogen is 2 times the atomic mass of hydrogen plus sulfur is 32. So that will give us 34 grams per mole. So in other words, moles is the measured mass over the former mass. So 13 over 30. So this is gram in a mole, so that the gram will cross and this one goes down. So if you check your answer, that should be approximately what?
0.384 moles.
0. What?
382
382
moles. That's correct.
Yes, sir.
So that is how we calculate moles for solid. Now, we also have variation from Avogadro, saying that if 1 mole is equivalent to 6.02 times 10 to the power, 3.
Say.
Happens to a different number of entities. Yes.
So please, in our schools, we used to write the mole in sometimes 1 decimal places and 2 decimal places, but our teacher will wrong us and tell us that we should leave it in 3 decimal places. So I was asking if here is different, or you know that you are doing it like this.
That teacher wants from. That's why I said approximately. So I'm saying approximately, it can be more or less. So I don't think it matters.
Okay.
I don't know where
Okay.
we're expecting YX to be giving you 3 decimal places. I doubt. Okay, so it doesn't matter.
Okay.
All that needs to do is to say it's approximately that. So I shorten that and I know it's approximately that. Okay. So if who gives us this, then how about the number of entities? So Avogadro says that, well, the number of entities, okay, should be equal to the moles times the Avogadro number. And this is also another relation you should keep in mind. So what it means is that we can break it down and say that once the moles is also mass over mass times the Avogadro number, it's also equal to the number of entities. So for example, now we have a mole of 0.4. what do you think would be the number for the hydrogen sulfide? So now we have the moles of hydrogen 0.4. I want to know the number of molecules in this hydrogen.
So we are getting 2.4 times 10 to the power 23.
Two point 408 times 10 is 23.
Okay. Yes. Now, say for example, let's say if I want the number of hydrogen atoms, can somebody help me? How do I get the number of hydrogen atoms from the hydrogen sulfide? What do you think will be the number of hydrogen atoms? Well, clearly you can see that the hydrogen sulfide is actually made up of 2 hydrogen plus 1 sulfur. So if I know the moles to be 0.4 here, then it means that the moles of hydrogen will be 2 times the moles of hydrogen sulfide, which is 0.8. So therefore, the number of hydrogen atoms is 0.8 times 6.02 times 10 to the power 23. Do you agree?
Yes, sir.
Okay. So we can get the number of atoms. But if you are following that, just a quick one, let's try to find the following. So how many moles will we have in 10.02 grams of calcium? How many moles would we have? Take calcium to be 40, so the atomic mass for calcium is going to be 40.08 AMU. So what would be the moles of calcium in this case?
Say most of calcium will be 0.25 moles.
0.255 moles.
So how did you do that? So the moles of calcium basically will be 10.02 divided by 40.08. This is grams in mole. So that will give you what? 0.25 moles.
25 moles.
Is that okay?
Yes, sir.
Well,
Yes,
how
sir.
about tell me the number of phosphorus molecules? So the number of phosphorus and that phosphorus molecules when it contains 92.91 grams. So when we measure 92.91 grams, what will be the number of phosphorus molecules that is contained in 92.91 grams? Well, the atomic mass for phosphorus is, if you have periodic table, please can you check for me? What's the atomic mass for phosphorus? So that is 1, 2, 3. Okay, so that's around
30.97.
Yeah, so the atomic mass for
30.97.
30.9.
30.97.
So let's say 975 AMU. So what's the number of molecules which is contained in the mass that you have weighed?
Number of molecules will be 4.48 times 10 to the power 23 molecules.
So how did we do that? So the number of molecules is basically going to be mass over molar mass times the Avogadro number. Do you agree?
Yes, sir.
The molar
Yes, sir.
mass cross 4 will be this one times 4. There are 4 of that, so times 4. That will give us approximately 123.9. Is that making sense? So that's
Yes.
that. So this means that it's 92.91 divided by 123.9 times 6.02 times 10 to the power 23. And he said he had what?
4.48 times 10 to the power 23.
4.48.
Yes, sir.
48 times
By 10 to the power 23.
92.
23 molecules.
23 molecules. I'll follow this. Okay. Now let's make it. The next one is to see whether the compound is liquid. Now, some surface also behave like, and that we call it. I don't want to remove anybody from this list. So that becomes so for example, if it is petroleum gas, it becomes a liquefied petroleum gas. Now what happens to liquid is that liquid is affected by temperature. Once you begin increasing the temperature, you are increasing the kinetic energies within the liquid, and of course the vapor pressure is going to be increasing the temperature. As the temperature increases, the pressure will also be increasing. So it's affected by temperature, it's affected by pressure. And so you have to calculate the amount this part of the Patrick team doesn't want to be part of that. So let me find a way of removing him from there. That okay. So I guess I'm just going to. I don't have that time to be going up and down. So please comfort yourself, mute your mic, and then that's yes. Okay. So for us to measure the amount of this liquid, and of course we measure liquid volume for liquid, and then for gases as well. So it means that we need to fix if we don't want the amount to be changing, then we have to fix the temperature at constant temperature, and then the pressure also at constant pressure. So we set what we call standard conditions. So we set standard conditions for that. When the standard condition is that we keep the temperature at 0 degrees, more like freezing that. So that's the 0 Kelvin. Then we'll keep the pressure also at 1 atmosphere. Well, some will say that we want to keep it at the room temperature, but then ambient temperature changes. It can be 24, 25 to 26. So we'll keep it at that. So if it's Kelvin, then we are keeping it at this standard Kelvin temperature and then atmosphere. So we say that we'll keep it at standard temperature and then pressure. Now, when we keep this temperature and pressure at a fixed kind of condition, at 0 degrees and then at 1 atmosphere, then we're going to have a volume which is also constant. Once there's no change in temperature, there's no change in volume. Then we can have a volume which is constant. And the volume which is constant for every liquid, once you keep it at 0 degrees and 1 atmosphere, will be 22.4 dm cubed. So dm cubed is also latest. So that becomes a fixed amount for every liquid that we have. And so for we to measure the moles or have the moles, we can equally say that the amount is just going to be the measured volume divided by the molar volume. So this is called molar volume. Okay, molar volume. So, which is, of course, the volume divided by 22.4 liters or dm3. Let's know the unit changes. Decimeter cube is the same. So, 1 decimeter cube is the same as 1 liter, and it is the same as 1,000 centimeter cube, and it's also the same as 1,000 millimeter cube. Okay, so mil means times 10 to the power 3, so that's just the same thing. Okay, so that's the unit conversion. Please take note of that. So if you have any liquid which you want to find or a gas which you want to find the amount, all we need to know is the volume that it occupies. Then the molar volume is constant, so that is decimeter in every 1 mole. So decimeter per mole, we can measure that. So this is 22 per decimeter cube per mole. That's constant. So that's how we can find the amount. So for example, a question is asked, how many moles are contained in 44.8 dm cube of oxygen, which is held in a container at a standard temperature of 2273 Kelvin and 1 atmosphere pressure? Well, the measured volume is 48.8 dm cube. Now at SCP, the volume or the molar volume at SCP, the molar volume, the molar volume is 22.4 dm cube per mole. So therefore, if I want the moles of that oxygen that is occupying that volume, then that will be the measured volume, which is 44.8 dm cube, divided by the molar volume, which is 22.4 dm cube per mole. Is that okay?
Yes, sir.
So then we can let's say that this is equal to 2 moles. So can you try this if I want to look at that? So it says that what is the number of molecules for this carbon dioxide gas which occupies 2.8 dm cube container? What is the number of molecules? Of course, we can find the number of molecules only when we know the number of moles. So the volume of the carbon dioxide which occupies that container is 2.8 dm cube. So what would be the number of molecules? As somebody else.
I'm having here 7.525
times 10 to the power 22.
10 to the power 22 molecules.
Thank you very much. How did we do that? Moles is volume over molar volume. The volume is 2.8 dm cube. So again, if the unit is not dm cube, try to convert them to standard units. And this is 22.4 dm cube per mole. And that, if I know the moles, now multiply by the Avogadro number, that becomes the moles. Does it make sense?
Yes, sir.
Yes, sir.
If the system is in a gaseous form where we are not setting standard conditions for that gas, so the volume changes whilst the temperature and the pressure is changing. Well, most of the gases follows what we call the ideal gas. And then the ideal gas, of course, we now have a law which governs the ideal gas, which we call the ideal gas law. And that was formulated by the Boyce, the Charles, and then the Avogadro. Now, Boyce says that the volume of a gas is inversely proportional to the pressure. Charles says that the volume is proportional to temperature. Then Avogadro is saying that, well, the amount of a substance is also proportional to to the volume it occupies. So if you put all this together, we have what we call the ideal gas law. Okay, which is P is equal to nRT. So it means that pressure is going to be changing while volume changes and temperature is also changing. There is what we call the gas constant. The gas constant. And depending on the unit that we are using, the gas constant can be 8.134, and that is joules per mole per Kelvin. Or we can use, commonly we use the 0 point. So always ask for that constant, 0.8206, and the unit is related atmosphere per mole per Kelvin. Okay, so that's a commonly used one that we use. So we can even say that then PV is also the same as M over big M times the R and then the T. Do you agree with me?
Yes, sir.
Okay.
Yes, sir.
We also calculate for the gases. Now put everything together. What it is that if I want the moles of a compound, if I want the moles of a compound, how do I get the moles of a compound? Say, for example, I know the moles of a compound. The moles of a compound can help me calculate the number of entities. The number of entities. So what it means is that if I know the number of entities, I can also calculate the moles. How do I do that? Well, if I know the moles, multiply that number of entities by the Avogadro number, which is Na or something which is L, then I can convert that to the number of entities. So we just have a factor that. Now, if I want the mass, can someone tell me how I can get to have the mass? So if I have the mass, if I want the mass of that compound, basically what it means is that I need to operate it with the molar mass, and then I'll get to have the mass. So the molar mass times that will give you the mass. Meaning, if I want mass, I just have to divide the moles by the molar mass. I mean, multiply by the molar mass, I can get the moles. So moles is mass over molar mass. If I want the mass, I multiply molar mass to get the mass. And if I have the mass and I want to get the moles, I just divide the molar mass by the mass to get the moles. The same way, if I have the moles multiplied by Avogadro, I'm going to get the number of entities. What it means is that if I know the number of entities, I just divide by the Avogadro, I'll get the moles of the compound. Does it make sense?
Yes, sir.
And now, please keep this in mind. As just the moles is just mass over the molar mass. Can also be the same as the volume over the molar volume. The condition here is that to be at STP before that will work. And it's also the same as PV to be equal to RT. We agree. So this is N, so N divided by RT. So we can spend time in trying to build up with this, calculations for moles. So calculating the moles of compound. Is that okay?
Yes, sir.
Let's do examples, then we can end it. And the question is that what is the mass of a substance that contains 1 mole of carbon-12? Can somebody help me answer that? What is the mass of the substance that contains 1 mole of carbon-12? How would we address that? But of carbon 12 is
12,
just
12.
that's all.
Yes, sir.
Is somebody saying something?
Is it 12 gram?
Yes, 12 grams is the mass of carbon 12.
Yes.
Okay. Now, I want to also, of course, when we're dealing with percentage abundance, so we can also use that to also see. So percentage abundance, I think when I was dealing with that, I didn't mention that I was just giving you the percentage abundance, but then for calculating percentage abundance, will just be the number of atoms, the number of atoms for that isotope divided by the number of for that. So let me rewrite that again. Okay, so it just linked to the number of atoms here. So if I want the percentage abundance of any kind of isotope, it's just going to be the number of atoms or the number of atoms for that isotope divided by the high number of atoms for the element. And because it's percentage, just increase multiply by 100. If it is fraction, I just leave it like that.
Yes, sir.
So please keep that eye for the
Okay, sir.
Now let's look at other moves and then see how we can calculate that. So for example, this is the law of conservation of masses. Okay. I'm trying to find a question for you, but then I think we have all this stuff. Quite interesting. We have more examples, but then, okay, let me see if I can get a few concepts here. A minute, let me find one. That's it, yeah. And then these are all the so please just remember this is it. I don't know if I don't have a book closer by where I can get examples of this work. Let me see from my paper if I can get it for you. Or somebody can bring a question if you have one, so we can all solve it together. If you have a question close to you which we can move, kindly bring it on board. Let's see. I thought somebody wants to give us some questions to solve. Otherwise, I didn't have any examples to give. Yes. Are you bringing a question? So based on the move concept, is there any question? Okay. Well, once we have the formula, the entire questions have exhausted that question. So the last, let me just give one example and see how it will go. So the number of entities for neon, the number of molecules for neon is given as 1.506 times 10 to the power 23 molecules. Now the question is that what will be the volume in which the neon was occupying to create this amount of molecules? What is the volume of neon when it contains 1.506 times 10 to the power 23 molecules? Can somebody help us? Yes. Oh,
Sir, please, the question again.
it says that what is the volume of neon which contains 1.506 times 10 to the power 26? What do you, how do we do that?
Sir.
Yeah, so neon is a real ideal gas, so the condition is that. So what will be the volume?
Sir, hello. 5.6. 5.6.
Volume will be what?
5.6.
How did you do that?
GMQ.
Yeah, 5.6.
So the
5.6
number
GMQ.
is mole times the Avogadro. Now at SCP, the moles is volume over the molar volume, which is 22 times the Avogadro, which is that, okay, 223 entities per mole. So basically, if I want the volume, then the volume will be the number of entities times the molar volume divided by the Avogadro number, or is that correct?
Yeah.
Okay, times 10 to the power 23. That will be the number, the volume which that gas occupies. I hope it makes sense. Okay, so that says that I don't want to exceed more, but then we can find the amount of these molecules or these compounds that we have named them, and then we can also proceed by putting these molecules together. So that's what we're going to be looking at from next week. When we put these molecules together, we are now going to form an equation. So we'll try to see what type of chemical equations are we producing. So we'll look at the chemical reactions, the type of chemical reactions that we have, so that it can help us predict the product. And then we'll also look at how this equation can be balanced. So that will bring in the stoichiometry, where we'll now find out some kind of relation from them. Please, any questions? Any questions? Okay. So
No,
thank
sir.
you. Thank you.
There will be no question.
So okay, my question is, it's not about like my question is like, when will we be having our first quiz?
Are you having your mind? Tomorrow? Is it tomorrow?
Tomorrow we don't have.
Yes, sir, we have
Come on, I didn't hear you. You're having it tomorrow.
yeah, tomorrow is match.
Time.
So from next week, you should be expecting your first week.
Okay.
So
Okay.
notice. But when I hear, I will also notify. At next week going, you should be expecting your first week.
Okay, sir.
Okay, sir.
Okay.